So the purpose of the lab that we're going to do today is going to be to verify the validity of Newton's second law. Now, why are we validating or verifying a law that obviously holds true? Because I told you so. Okay, that's why we're going to do it. We want to make sure. I mean, in science, you're always confirming things. No matter how many times they've been proven true, they can still be proven wrong. Okay, so we want to make sure and verify that Newton's second law is going to hold up and behave the way we predict. Okay, so the background is, okay, that obviously Newton's second law says acceleration of an object is related to the net force and the mass of the object. Any increase in the net force will result in an increase in acceleration. Any increase in mass will result in a decrease in acceleration. Okay. So we're going to have a set of hanging masses, as you see in the diagram here. We'll have a set of hanging masses and the cart. Okay, the cart will be tied to the hanging masses with a string that's stretched over a pulley. Everybody with me there? Okay, how many different masses are in this system? Yeah, essentially there's two groups of masses. Okay, there's the mass that's hung over the pulley, and there's the mass that's the cart plus whatever mass is on the cart. Okay, if I'm going to do an experiment like this, where I want to alter the applied force, okay, which is going to be essentially the net force, not quite entirely, but essentially the net force. Okay, if I want to test the effect of changing that force on the acceleration of the cart, what do I need to make sure stays the same throughout this entire lab? Okay, I don't want to change carts. Yes, I was thinking something else. Something. No, I want the velocity to change. I'm measuring the acceleration here, right? What I'm doing here, guys, I want to test the effect of a net force, okay, in this case, the applied force, on the acceleration of the cart. But the cart's part of what? A system. So what other thing could change the acceleration of the system if I change it? The mass. So I need to make sure that the mass of the system stays the same throughout all the trials. Otherwise, a change in mass is going to cause a change in acceleration. Agreed? Okay, so the idea here is that I want to change how much mass is hanging over the pulley because I'm using gravity to apply the force. But if I put more mass here, that changes the mass of the system. Unless I take it from where? The cart. Okay, so I'm going to have to make sure that my system always has the same mass. All I'm going to do is change where in the system that mass is located, right? In order to make sure that the mass of the system remains the same. By changing where it's located, that is taking it off the cart and putting it over the pulley, I can also then change the thing I want to change, which is the force acting on the system. Everyone follow me there? And then I'm going to look at and measure and record the resulting acceleration. All right, there's my very cryptic way of giving you essentially every variable in the design part. No. Oh, I'm not going to tell you that. This was my very cryptic way of giving you all the variables in the design part. That's as much as I will say. Okay. There's only one manipulated variable. There can only ever be one. Otherwise, I don't know what's causing the change, right? For your responding variables, there's one that's very important. There are other things that are also changing that we would want to probably list, but there's only one that's really important to what we're doing, okay? And then, obviously, we need 3 controlled variables, okay? I kind of gave you one. Think of some others that could affect this, okay, that we want to keep the same. All right, so for our hypothesis, okay, we want an if, and then statement. Since the premise here is Newton's second law, the if part should probably talk about Newton's second law. What does it say about the effect of a net force on the acceleration of a system? Okay, that's what the if part should say. If Newton's second law says this, okay, that's what we're trying to confirm. Okay, the and part talks about the experiments, right? The driving force on a system will be increased and the acceleration will be measured, whatever you want to say. Okay, that's essentially what we're doing. right? In the then part, you need to predict your results. If Newton's second law says this, and you do that, what's going to happen? Okay, and specifically, I mean, what's going to happen to the acceleration of the system, right? That is, after all, what we're measuring. Okay, so we need to say what's going to happen. That way, we're either going to be right or wrong. Okay, there's not going to be an in-between. Results. That's not how you spell results. I crossed my L and dotted my T. Results. There we go. Okay, so what we're going to have in this setup, and we only have 4 ramps that we can do that with, or do this with. Okay, we have to use the fancy Pasco ramps. Okay, so there's only 4 of those, so groups are going to be kind of big here. What we're going to have is the motion sensor that we've always used, okay, that kind of triangular thing, and it will clip right on to the end of the ramp. And I didn't grab those. Okay, so they've got the little gap here that someone wrapped the cord into. Okay, with these little metal tabs. Okay, it's designed to do this. Okay, it just slips right on to the ramp. Okay, so just make sure that it's on there, and obviously that the motion sensor is pointed down the ramp. Okay, so that'll be the first part. Okay, you will have a pulley that will go on the other end. Okay, now these pulleys are plastic and they screw on, but they screw on with tension, so you may actually have to take a piece of paper and fold it up in order to get this tight, because the ramps are not very thick. So you may have to put a piece of paper in here and then screw it onto the bottom of the ramp, okay, just to make sure that it's tight. Okay, the pulleys are really good, and you can adjust the angle if you find that the string is rubbing anywhere. Okay, but they've got really good bearings. They're essentially frictionless. Okay, they spin and spin and spin and spin and spin for a really long time. We're not going to wait for it to stop because it takes a long time. Okay, but there's not very much friction in those pulleys. All right, so we will run the string over the pulley and tie it to the cart. We have to use the silver carts this time. Okay, that's these ones, and they have a hole at the front and another one at the back, but it's full. Okay, so tie the string through this hole, okay, onto the cart. Everybody with me there? All right. Some of the carts have sticky tack on them already. If yours doesn't, I have a small supply of it right here. You need to have sticky tack on the top of the cart. What for? Yeah, you got to hold the masses on, or Newton's first law will come into full effect as soon as the forces yank on the cart. The masses will stay still, the cart will slide out from underneath them, and the experiment won't go very well. Okay, so the masses actually have to be stuck on to the top of the cart. Okay, so we'll have that. Okay, we'll have them tied on there and then over the pulley. Now, you're going to be doing this on your desk. Is your desk level? Not perfectly. So my suggestion is put the ramp on there, take your phone out, and there's a clinometer, like a level, on your phone. Okay, it's one of the apps that comes on your phone. Stick your phone on there and make any adjustments you need to make to the ramp in order to make it level. My suggestion would be put it across 2 desks. Okay, on just one desk, okay, it's going to be a lot more difficult because you'll only have part of the ramp on the desk. So put it across 2, and then just have the edge hanging over the second desk. Okay, now how much string do you need? You need as much as it would take for the mass to fall from desk level to ground level. Okay, I once had a group who used the long ramp, and someone's going to have to use the long ramp, and they pulled out a piece of string that was as long as the ramp. We don't have that much string. Okay, so don't pull that out. You can only use gravity to accelerate the cart as long as the masses are falling. Once they hit the ground, they're no longer exerting any force on the string. Okay, so you can only have this work until they hit the ground, so you only need that much string. That may mean that your cart actually starts like somewhere in the middle here. Okay, you can put as much string as you need to put it back by the sensor if you want, but know that it's only going to accelerate as far as the masses can fall. Okay, If you're using the big long ramp, please don't use the whole big long ramp. Okay, it takes forever, okay? And it takes a lot of string. Question? No, you're just going to use one kind of mass, okay? And it's all these little hook masses. Another thing I forgot to bring out, okay? So you're going to be using these masses, okay? And all you're going to do is stick them on the cart. Yeah, okay? Then we move mass over the pulley as need be. You're not going to be using one this big, okay? Everyone all right with that? Okay. All right, so the string is over here on the table, okay? We have some of the yellow and some of the green. I need you guys to save the string so my afternoon class can use it, okay? So whatever string you use, just roll it back up like on your hand or something and just put it in a pile next to the pulleys, okay? So that, because someone stole our string. We had a brand new roll like this and it's gone. Somebody borrowed it, okay? Was it? Probably. Okay, so that's the stuff that you will need. That's the setup for it. Now, the procedure will go as follows. Okay, we are, like we said, going to move masses around. Now, the mass of each one of those silver carts is 502 grams. I tell you that because you need to know it, and then you don't have to measure it. Okay, it just takes a lot longer when we're measuring the mass of those carts. Their mass doesn't change. They're 502 grams. Okay, then you're going to have the mass of the hanging masses. So it will have mass of the cart and the masses we put on it. Okay, mass of the hanging mass. Okay, applied force. That'll be your hanging mass times 9.81 because it's providing the driving force here. Okay, and then we'll have the acceleration, which you're going to get from making graphs. Okay, so you're going to build graphs in Google Sheets of each one of your trials, right? And what you should see is an ever increasing slope, okay, for each trial as we increase the amount of mass that's hung over the pulley. Okay, everyone all right with that? Okay. And again, Google Sheets will spit that out for you. All you have to do is just plot the data. All right, it'll be a velocity versus time graph for each trial. Get the slope. That's all you need from that graph. You're not going to do any other calculations to do with that graph. You just need the slope from it for this. Okay. Then you're going to calculate the net force. So you're going to take the mass of the system. So that'll be this plus this. Okay, mass of the cart and masses plus the hanging mass, mass of the system, times the acceleration. Theoretically, net force and applied force should be the same. Right. Are they going to be? No, they're not. They're going to be close, but they're not going to be exactly the same because there are going to be forces that we haven't taken into account. All right. We're going to do our best to take them into account, but they're still going to be there and they're still going to have some effect on the experiment. One of the things in the analysis that you're going to be required to do is to look at your net force and your applied force and decide what forces really affected my experiment. Okay, you'll have to figure out what forces were involved. Okay, and then tell me how did they affect the experiment. That's part of the analysis. Okay. All right. So what we're going to do here, okay, is in trial one, we're going to have the cart plus 400 grams. Okay, so we'll have 400 grams worth of mass on top of the cart. Okay, and we'll have 50 grams hanging over the pulley. In the second trial, we're going to take 50 grams off of the cart and move it over the pulley. Each trial, that's what we're going to do. We're going to take 50 grams off the cart and put it over the pulley. Now, you don't have enough masses to put that many 50-gram masses on the cart. You'll have to do a little bit of math. Okay, like the first time you could move a 50-gram mass, but the next time you might have to take that 50-gram mass and switch it with 100. Okay, whatever. You're gonna have to figure out how to do that. Okay, so you'll need to do those are the numbers that you're going to use, and then you'll be filling in the rest of these numbers in the chart. Okay, but these will be our mass numbers for trials. Each trial moves 50 grams from the cart over the pulley. Okay. Preservation of equipment / safety tip. Somebody needs to catch the cart. Okay, there has to be one person whose sole job is to stop the cart from hitting the pulley. If the cart hits the pulley, not only will it destroy the pulley, but the cart will jump over the pulley and it will land on the floor and it'll break. And then you'll be in big trouble because the carts are not cheap. Okay? We know because we were just shopping online on Friday in CLC time looking for replacements for them. Each one of these stupid little carts is over $400. Okay? Yeah, it's incredibly dumb because now they have the sensors that we have embedded in them, built in, because that makes them more expensive. Yeah, that's how, unfortunately, things work. So please be careful with these. We don't want to have to replace them with the sensor ones that have the the sensors embedded in them. They're too pricey. Okay, and we can't get these anymore because that's good business. Prevent people from buying the cheap ones by not making them anymore. Okay, so just be mindful of that. Someone's job is to catch the cart. Now, when you are releasing the cart, again, you don't want to get your hands in front of the sensor. Okay, so hold it kind of down below and from the side. Okay, have the person who's running the app tell you when to release it. Release it. The other person catches it at the end. Okay, question.
Is there any specific amount of digits you want to run?
No. I don't have any specific number of digits I want it rounded to. It'll work. Yeah. Okay. All right. So yeah, 4 trials. Plot them all on the same graph. Okay, and build your graph so you get the slope, and then you're off to the races from there. Okay. So your graph. I mean, it's not going to look like this because this is an older one, but okay. Obviously, the lines are going to get steeper and steeper as we do this experiment. Okay. For your analysis. So question number 1 is just about putting a best fit line for each trial on your graph and getting the slope. Okay, calculate the applied force, put it in the table. So just another simple calculation: mass of the hanging masses times 9.81. Okay, using the formula described in the background, calculate the force on the cart using the mass and acceleration of the cart. Okay, so again, that's doing your m times g. What's the relationship between net force and acceleration? Okay, so talk about that a little bit. Did it go up as you increased? Okay, draw a free body diagram that describes the forces involved on the cart and the hanging masses. Right, so I'm going to want to see a free body diagram that shows the hanging masses, the cart, and then this is where you identify those forces. So you'll have calculated your net force already, compared it to your applied force, and you're going to go, okay, is this force involved? Was that force involved? Which way did it pull? How did it affect this? All of that kind of stuff. Okay. And then in number 6, the net force and applied force are not equal in value. They're close. Okay. Explain why this is the case using your knowledge of Newton's second law. And so you're going to be explaining your free body diagram in question number 6.
Do you want to draw it and take a picture and put it in?
However you want to do it. If you want to draw a picture of it and then snap a picture and insert that picture, I'm fine with that. Just as long as there's a free body diagram in there. If you want to draw it using Google Drawings, good on you. I would draw it on paper and take a picture of it because that's way easier. No, I don't want any paper. It's only coming electronic.
How many graphs do we use for today?
Just make one graph with the 4 trials on it because all you need is the slope of each line. Okay. All right. So that's the analysis. Okay, and then as always, conclusion: restate your hypothesis, explain why you can accept or reject it based on what happened, sources of error. Okay, how can you eliminate them? Okay, that kind of thing. All right. So again, we're gonna have big groups because there's only 4 ramps. Okay, so make sure there's enough room. We don't have to leave the room here. Everyone can do this lab in this room. Okay, just find a couple of desks to put your ramp, or not your ramp, shouldn't be a ramp, should be flat, okay, across and get going on that. Okay, if there's trouble, let me know. Remember, using the SparkView app, you need to have the SparkView app closed when you connect to the Bluetooth transmitter. Okay.